Hey everyone, back again with another exciting lecture from your professor. Um, Last one over flooding and streams, I know was a long lecture, so I am definitely going to cut this one shorter on coastal processes. This is a very important chapter as well, however, it's explained really well in the book, and again, I want to give you a little bit of a break. So we're going to rely heavily on the material in the textbook for your studies, and I'm going to make this, I'm just going to hit some highlights on coastal processes, just kind of the most important points in this slideshow, and then if you have any questions, you can ask. So coastal hazards are something that are pretty well known. We see them in the news a lot. Of course, we don't have those around here in Kentucky, but they're pretty big drivers as far as natural disasters go. You have different types of coastal processes that happen. Coastal hazards, some of those are climatic, like hurricanes and big storms. Some of those are erosion driven, and some of those work in conjunction with one another. Now, one of the reasons that coastal hazards are so well known and heard about so much is because a lot of people live near the coasts. If you look at population densities in the United States, especially, but really all around the world, you have high concentrations of people that do live around coastal areas. So when there is a big problem around a coastal area, people are really affected by those, generally speaking. On this slide, we talk about sea level not being static. Sea level adjusts, as you have probably all heard for your entire lives. We hear about climate change and rising sea levels. And this is just an example. This slide is showing the shoreline was 110 feet lower 18,000 years ago. So that means that that was a glacial time period, that more of the water was taken up in ice, in glaciers, and in the poles. So, and sometimes it's higher. 3 million years ago, the Earth was a lot warmer and sea level was a lot higher. We had a lot less land than we have now. Right now, it's increasing noticeably as our temperatures warm during climate change, and for all intents and purposes, unless something just crazy happens, it's going to continue to do so for the foreseeable future. That's one thing about climate change. We mentioned something called lag time in the last lesson about floods having a lag time. Well, climate change is going to have a lag time too. Even if we stopped, if humanity disappeared tomorrow and we stopped emitting greenhouse gases into the atmosphere, it's going to take the Earth time to rebound from that. As a matter of fact, it's going to keep warming for a while until that would stop if we disappeared even. So regardless of what we do in the coming years, which by history, if you study history, it's probably not going to be much anyway. But even if we did decrease our fossil fuel use and be greener on our energy, we're still going to have a lag time that the temperatures are going to continue to rise until something pretty big breaks that trend that we're going in. So shoreline characteristics, of course, the shoreline is where the ocean meets the land, and you have what's called leading edge shorelines and trailing edge shorelines. Basically, leading edge shorelines tend to be more mountainous shorelines in tectonically active areas. In trailing edge, you're going to see your flatter, longer, more consistent beaches in flat-lying areas along the coast. So if you think about California, which you know is tectonically active from our previous lessons, is going to be a leading edge shoreline, where somewhere like Florida is going to be a trailing edge shoreline because it's flat, uniform, linear beaches, and here you see those two different characteristics, different types of shorelines. So you probably heard about tides. We have low tides and high tides each day in the ocean. There are several factors that contribute to that. I'll let the textbook explain those mostly. But basically, because of the spinning of the Earth, the oceans actually bulge in the center a little bit, and that pushes out toward the continents. So you get that bulging effect, plus the gravitational pull of the sun, and more importantly, the moon when it comes to tides, affect high tides and low tides and how those operate in conjunction with one another. So you can read about that a little more in the textbook, but that's just a general overview of the tides and why they form. Currents, we have different currents in the oceans. Now, when we talk about coastal processes, we have tidal currents that are working pretty close to shore. Wind currents, of course, that's which direction the wind is blowing, has an effect on how the water moves across the surface. And the density of water. Density of salt water, fresh water have different densities because of their chemical makeup. So you have areas that will flow toward or away from each other based on their densities. And remember, it's a theme over every lesson since a couple lessons ago. Nature is trying to move toward that equilibrium, that baseline. So anytime you have differing densities of water, just like temperature, just like any other thing we've talked about, they want to move toward each other to equal each other out. So you're going to see those ocean currents really form due to the density of the water. So waves, we all know waves are common in the ocean. They happen all throughout the oceans on the planet. This is just a cross-section of waves and how we define waves. You can see the wavelength is the distance between the crest of two waves, which the crest is the top of the wave, the trough is the bottom of the wave, and you see a little bit of movement, a circular movement, as the molecules work in a circular motion as they go deeper and deeper to the wave base. And you have wave heights, that's how we measure waves. And as it gets closer to shore, I want you to, as we're talking about this, think about a tsunami, which is an extraordinarily big wave, and why it is so destructive on the coast when it hits the coast. So if you're out in the middle of the ocean, the waves are actually further apart. Their wavelength is longer out in the middle of the ocean because the water's deep and there's no friction or anything happening. So they're pretty consistent out there. Even though they might be bigger or smaller, you don't really notice it as much like a tidal wave out there. I mean, you would notice it a tidal wave, but it's not going to be as big of a difference as it would be on the beach when it gets to the close shoreline. So as that wave that has this molecular movement under it, kind of like a little washing machine under it, just cycles around in a circle, as it gets closer to the shore in shallower water, there's friction that starts to happen on that wave because it's dragging across the bottom. That little circular motion is catching the bottom of that wave base, down the wave, you see the wavelength there, the wave base. It's hitting the wave base, and it's starting to distort that wave a little bit. So the wavelength gets shorter as that distortion happens when it gets closer to shore, and the waves get taller. They gain in height. So when you get a tsunami or a tidal wave that's out in the ocean, as it gets closer to shore, it actually gets taller than it was out in the middle of the ocean. And that's not good for the people on the shoreline. So as these waves get closer and closer in shallow water, that friction for on the bottom, especially if it's irregular, but both on the regular bottom as well, even if it's pretty flat, you're going to start to have those irregularities, and they sort of refract a little bit. And as they refract, think about it like this. Think about a wave, even though waves are consistent. Think of it as 100 meters long. So one end of the wave is going to refract, and it's going to get to the beach before the other end of the wave does. It's going to go in kind of a linear motion. And when that happens, the waves start to break on each other. So that's why you see waves crashing over, and they call them breakers or breaking waves. So as that happens, two things happen. One is, as that wave has refracted, and say this end is hitting the beach before this end, you get what's called a longshore current. That means there's a current kind of riding down that angle. And then you also have, as you have these sand particles that move along the shoreline, you get an action of a back and forth, kind of a zigzag. And what happens is, if you think about this, most all of you probably have walked on a beach before and kind of at least somewhat paid attention to the waves. You know, when the waves break and they wash up and go as far as they can up on the beach, they kind of cover the sand with water, and there's sand in that water, and then they recede back down, kind of up and down and up and down. And as that's happening, it's actually moving those little grains of sand kind of sideways, because if you really pay attention, those waves aren't hitting straight from a perpendicular angle, like straight horizontally. There's a little bit of an angle to them. So these sediments are actually traveling in a zigzag pattern, up, back down, up and back down, all the way up and down the beach. And it depends on what direction this longshore current is going in as far as where this sand is traveling, either traveling this way or the other way, depending on which direction that current is. So some of these, I'll let you again read some of these in your textbook. You have differing effects on beaches and shorelines depending on what types they are. In the previous example, we were pretty much looking at just a Florida type trailing edge beach. Here you see more of the mountains, the leading edge beaches with tectonic activity close with mountainous areas. And you're going to see a lot of coves in these areas because the rates of erosion are more irregular against the rocks. But you're also going to see these points. And typically those points are highlands or higher areas that form. And as these waves come in and hit, they refract around these points and kind of hit it from all sides. And as that happens, it's breaking away little particles that become sand, and that sand washes into the coves. So in a place like California, your beaches are going to be more split up, and they're going to be inside coves instead of a straight, linear, uniform beach like you have in Florida, for instance. And again, this kind of shows this shoreline evolution as it's happening. And as you can see, just generally, if you look down this list, over time, we're going back to that baseline or that equilibrium. Over time, we're talking geologic time, millions of years, that coastline wants to erode down to that equilibrium like you see, for instance, in Florida, where you have a linear, pretty uniform beach area. Barrier islands, pretty simple. This is just a depositional feature that you see, especially along the coastlines of places like Florida, where you have that type of uniformity. These are really attractive for development, as you can see in the picture down here. This is a barrier island. You see hotels, really nice areas for people to go on vacation. However, once you learn how they're formed in this chapter, the sand, the tides, the susceptibility to hurricanes and storms, the erosion, these are actually probably the worst places to build anything with regards to human habitation. They're very unstable. They're very susceptible to storms and erosion and weathering. And you're just looking at problems when you build on these things. But we were going to do that because people make money by building on these things. So now we're going to get into the storms, the climate, the hurricanes. So you might hear in the news, of course, you hear a lot about hurricanes. Sometimes you hear about typhoons, and sometimes you hear about cyclones. They're all the same thing, basically. They're all tropical storms, weather systems that form low pressures from evaporation of very warm water, intense low pressure storms, and they move generally away from the equator. Now, the reason they have different names is strictly based on where they are geographically. Hurricanes form in the Atlantic and move toward North America, and also we call hurricanes that form in the Pacific near Central America that move north and somewhat west out in the Pacific Ocean. So we call these areas hurricanes. Now, just west of this, if they start their formation in the middle of the Pacific and move toward the continent of Asia and points northward, then they're called typhoons. Again, the same type of storm. It's just a different name. Now, storms that form in the Indian Ocean on both sides of the equator, north and south, that move westward again, but westward on the north side of the equator means they move westward and somewhat northward into continents of potentially Africa, but more than often than not toward India and southern Asia. And then south of the equator, they move west and south. Basically, most of these move out in open ocean. We don't hear much about these at all. The ones that hit India and Bangladesh, where you see the cyclones right here in red, where my pointer is, are devastating because of the high concentration of population there and the landform, the way the geology is there. It's just big catch basins of these storms, and it just devastates the population there. Here is a cross-section of a hurricane. You see where the extreme low pressure, the evaporating warm water is going up around the eye of the hurricane. It gets up here, starts spinning around, and then you see the convective winds in the middle of it here. So the biggest hazards we have with hurricanes, there's three: storm surge, high winds, and inland flooding. So high winds, everybody knows what winds do. Here you see these are pictures from one of the hurricanes. I don't remember exactly which one is which, but you see the devastation. The high winds have destroyed homes. You see a piece of plywood driven through the middle of a palm tree here. Just the winds are just ridiculously strong. So that's the first big danger, and that's the one that we most commonly think about with hurricanes. The other two are storm surge and inland flooding. And a lot of people that don't study this really don't know the difference. They just know they're both high water, which that is true. They're both high water. Inland flooding, we just talked about flooding before in our previous lesson. So that's from the precipitation that happens in association with that hurricane. It dumps over land, and all the rivers and water bodies are completely flooded. They're inundated with water. It's too much that they can handle. Typically, these are low-lying areas, and they are just inundated with water from flooding. Storm surge is different. Storm surge is also a type of flooding, but it's from the ocean. So what happens is, and especially on the northeast corner, because of the way the winds circulate around the eye of the storm, we just talked about our tides. We have low tides, we have high tides. If a hurricane coincides with a high tide in a certain area, it can be very devastating because, again, we talked about that bulge in the ocean just normally during a high tide. In addition to that, if we go back, this low pressure system here, because of it's sinking here, but then it's wrapping around up the sides of it, it's kind of sucking the water with it. It kind of creates another bulge in the ocean right there on the coast. And that coincides with the winds blowing. Of course, the winds affect the tide as well. And all those things come together, and you can have a tremendous storm surge that goes from the ocean inland. Think about, it's kind of like, I don't want to say a tidal wave. It's not that immediate and that quick, but it just rises up, and sometimes we get up to like 30-foot storm surges. That's not unheard of. So again, here's the storm surge. You kind of have that dome of water that's being sucked up around the eye. And the northeast side, because you have a counterclockwise circulation, it's driving this water in to this northeast corner, and it's pushing all that tide up onto this beach right here. Depending on what kind of land that is, if it's Florida, it's flat, it's going to go pretty far inland. If it's a mountainous area, it might not be as bad. It would be just as bad for the people right on the coast. But we don't have a lot of mountainous areas on the eastern United States coastline that are going to get hit by hurricanes. This is from a storm surge in Texas in 1900. Galveston, it's estimated that almost a third of the people that lived in the city died in this storm surge. They're not sure exactly how many, but it could be up to a third of the people. Everything that was constructed near that beach was just completely destroyed by the tides. And here is just some images on forecasting. Of course, with our technology today, our meteorology, we have a really good handle on from the time these things start to develop to their potential paths. This is just kind of a diagram showing the potential of hurricanes hitting a specific area, major and kind of normal hurricanes. Hurricane paths that we see here, they can track them. You see this one goes all the way up through Kentucky. Of course, by the time it reaches Kentucky, it's not a hurricane. This is Katrina. This hit New Orleans. This was the one that was so devastating to New Orleans. And they track it all up because it remains a tropical system until it gets up into the continent. So it might be a Category 5 hurricane here. By here, it might be a Category 1. By here, it might be a tropical storm still and a tropical low pressure by the time it gets up here. But they'll track that all the way up because even though it loses its punch with regards to storm surge and maybe the intense winds, it still has a lot of precipitation with it. So, and of course, up here we can see a cone. They can kind of determine approximately where this hurricane is going to hit from the time it forms. We've gotten really good with this. Frequency of hurricanes, you can see here, this is just a bar chart, but you can tell that in general, we've been increasing over time. Since 1996, it's increased quite a bit than before that, both tropical storms and hurricanes. It doesn't really show it on this graph. Let me see if there's another one. But the intensity of these storms has increased quite a bit. We're getting more high-end category storms, more 3, 4, and 5 storms than we did in the past. Here is Hurricane Katrina, the one that devastated New Orleans. It was a Category 5 until just before it hit New Orleans. It dropped to a Category 4. But because of where it hit and the time with the high tides and everything involved, it hit right in the worst spot it could have for New Orleans. And here you see a side-by-side photograph of this same lake before and after, or different years, but this shows the water levels in that event. So what can we do to mitigate these things? Of course, again, like flooding, don't build in certain areas. It's better for us not to build if we know something's going to get destroyed if something happens. So avoid building. Having better plans, for instance, in Florida, if you know you're going to go through hurricanes, construction should be more stringent as far as how you put roofs on houses, the materials that you use to make them more windproof as well as you possibly can anyway. Better aerodynamics. You can see here how the wind flows over the house instead of into the side of the house. Those kind of things need to be taken into consideration. Continue to improve our forecast and our warnings, and have good emergency plans in place, and educate the public. Let them know if we say you need to leave, you need to probably leave. It's a good idea. And sometimes that storm might move a little bit. It might not hit a certain area. That doesn't mean it wasn't a good idea not to leave, because you just never know. Again, you see here mitigating storm hazards in construction. I'm not going to go into great detail on that. Tsunamis, we've mentioned briefly in a couple of different lessons. Again, these are hazards from the ocean, and they are caused by either mass wasting events, if you remember, volcanoes or earthquakes. Anytime a large amount of ocean water is displaced, you can have a tsunami form, and it can affect somewhere thousands of miles away, because it can travel across the entire ocean. It doesn't have to be right near where that event happened. It doesn't have to be right near where the earthquake happened. It might be across the ocean on the other side. That wave can carry that far away. And here you can see the effects of tsunamis. The earthquake was actually here, but you can see everywhere that was affected by tsunami. This was the one in 2004 in Indonesia. This is a before picture of a spit on a coast on one of the islands. You can see it before, how built up it was. After, it's gone. Everything is gone. It inundated and destroyed everything on that piece of land. So early warning systems, we have these in place. These are buoys. They detect waves, and we have them all around the world on coastlines. And that will help us to have an early warning system. Say an earthquake happens here, you might pick that wave up on one of these buoys, and you'll continue to pick it up as it goes across the ocean along these buoys. So you know if it's intensifying or getting smaller, or if it's there at all, we can kind of track that and warn people along the coastlines. And again, this is the same tsunami that we saw before. It just absolutely just wipes clean the entire coastal area. And you can see here, this is actually a mountainous area, but anywhere that was flat that had construction, it completely just destroyed everything. And there's plenty of videos on this out there online. I included a video in our lesson about it. It was pretty scary and remarkable, the power of that tsunami. Rip currents, you might have heard of a rip current when you've been swimming at the beach, how dangerous they are, and they are indeed dangerous. That's basically when you have some type of irregularity on the bottom, and it allows the current, the ocean, you have the currents moving along the edge of the beach, and there's an escape route for them to get out, and suddenly you'll have both waves getting sucked straight out into the open ocean. That's basically what a rip current is. You can see a picture of it down here. Now, these are kind of similar to currents that we get in whitewater sometimes. We're on a much smaller scale, obviously, because we're in a river, not in an ocean. But biggest thing to do here, if you ever get caught in a rip current, your nature is to try to swim back into the shore, but that's like swimming on a treadmill. You're going against the current. You're not going to do anything. What you're supposed to do is swim side to side, straight sideways, and eventually you should be able to get out of it. I'm not going to go through this that much. Shoreline retreat, that is basically just the eroding away of shorelines. You're taking away beaches. Sea level rise from climate change is definitely affecting this. Again, they discuss this in your textbook really well. I'm not going to go into a lot of detail on this. These are some of the mitigating effects of shoreline processes. You've got sea walls, barriers, jetties, and here is an area with a water breakwater, whatever you want to call it. That's an area, it basically cuts off ways. If you've ever been to a lake and you see a floating mass of material around a boat dock, that's basically what that is. That's cutting those waves down so it's not bouncing that dock up and down. Same process here. This is going to be a little bit more sturdy structure than you see around a boat dock in a lake. But what it's designed to do is cut the waves down so they don't crash into the shore as much or as hard as they typically would. And you can see here around the edges of that, you're going to get more erosion because you're following this water to the side instead of letting it take its natural course there. And here you can see a before and after picture of some mitigation efforts. And that's it. Like I said, I wanted to make this one a little bit quicker and rely on the textbook materials just a little bit more since the last lesson was so long. The next chapter is going to be water resources. I'll talk about karst and things like that a little bit more in there as well, so that one might be a little longer too, but then we'll get back to kind of normal after that. Water resources is just a very important topic for the entire world, especially around here in our local environmental endeavors. So thanks, and as always, if you need anything, just let me know.